AI, machine learning, deep learning, generative AI. You've heard these terms thrown around everywhere, right? But what do they actually mean? And more importantly, how do they all fit together? Well, don't worry, we're going to cut through all the noise and build a really simple, clear roadmap starting from the very basics and going all the way to the incredible creative tools you can use today. Okay, to really get what's going on, you have to understand this one fundamental shift. For, decades, programming meant a human writing out a perfect step-by-step set of rules for the computer. If this happens, then you do that. Simple. But with AI, we totally flip the script. We give the machine a bunch of examples, the inputs and the outputs we want, and we tell it, you figure out the rules. And that right there, that's the core magic we're going to unpack.
So let's start with the biggest idea of them all, the AI umbrella. Think of this as the entire universe we're about to explore, from the very outside.
Now, this diagram is the perfect mental model for everything we're talking about today. Seriously, picture it like one of those Russian nesting dolls. On the very outside, the biggest doll, you've got artificial intelligence. It's the whole field. Then you open it up, and inside you find machine learning. Go one layer deeper, you get to deep learning. And right there at the very core, the tiny doll that everyone's excited about right now, that's generative AI. We're going to work our way from the outside in.
So let's start at the top, artificial intelligence, or just AI. At its heart, AI isn't a single technology. It's this grand old dream of computer science, to build machines that can think, reason, and act in ways that we would call intelligent.
And what does it mean to simulate human intelligence? Well, it means building systems that can do all of these things we do without even thinking about it. Stuff like reasoning through a problem, learning from experience, perceiving the world through sight and sound, understanding what we're saying, and, ultimately making a decision. These are the huge, ambitious goals of the entire field.
And look, this isn't just science fiction anymore. It's totally woven into our daily lives. Every time you ask Alexa for the weather, or you see a car parallel park itself, that's AI in action. Even a computer program that can beat the world's best chess player, yep, that falls under this big umbrella too.
Okay, so if that's the big picture goal of AI, how do we actually get there? Well, for the last couple of decades, the most powerful answer by far has been machine learning. We're now zooming in one layer. You can think of ML as the powerful engine that drives almost all of modern AI.
And the name really says it all, doesn't it? Instead of giving a computer a super rigid set of instructions like we talked about, we do something way more powerful. We just show it examples. We feed it tons and tons of data, and we let it figure out the patterns and the logic all by itself. It learns from experience, basically, just like we do.
You see this working every single day. Think about your spam filter. Nobody programmed a giant list of spammy words into it. Nope. It learned what spam looks like by analyzing millions of emails that people like you and me marked as junk. It's the exact same idea behind Netflix knowing what show you're going to want to binge next. It's all about learning patterns from data.
And it turns out there are really three main ways these machines can learn. First, there's supervised learning. The analogy here is perfect. It's like learning with an answer key. Then you've got unsupervised learning, where we just give the machine a giant, messy puzzle and say, find some patterns in here with no hints at all. And finally, there's reinforcement learning, which is basically learning through trial and error, getting little digital rewards for good choices and penalties for bad ones.
All right, let's peel back another layer of the onion. Inside this world of machine learning, there's a super powerful, really sophisticated approach that has changed absolutely everything. It's called deep learning.
Now, deep learning is where things get really, really cool. It's a special kind of machine learning that's actually inspired by the structure of the human brain. It uses these complex things called neural networks with many, many layers stacked on top of each other. And that's the deep part. This layered structure lets it find incredibly subtle patterns in huge amounts of data that older methods would just completely miss.
So why is this such a big deal? Because these layers let the model teach itself what's important. A human doesn't have to tell it what to look for. This breakthrough is the foundation for almost all the crazy AI stuff we see today, from systems that understand language to ones that can recognize what's in a photo.
And the results? I mean, they feel like magic, right? The reason your phone can recognize your face from a weird angle, or why Siri can understand what you're saying even if the TV is on in the background, is because of deep learning. It handles a level of complexity that older systems just couldn't touch.
Which brings us to the very center of our diagram, the little doll in the middle that has captured everyone's imagination. Let's talk about actually creating stuff with generative AI.
Okay, here is the big twist. Everything we've talked about so far, AI, machine learning, deep learning, it's mostly been about analyzing data or making predictions about things that already exist.
Generative AI flips that completely around. It uses everything it's learned to create something brand new, something original. It doesn't just understand art, it can actually make art.
And the stuff it can create is just astounding. I mean, we're talking about everything from drafting a quick email or writing a beautiful poem to generating a stunning piece of art from just a sentence, or even writing working computer code to help out a programmer. It's become a tool for creation in almost any digital medium you can think of.
And of course, you know these names. Tools like ChatGPT, DALL-E, Midjourney. These are where all those concepts we talked about, AI, ML, and deep learning, all come together into something real that you can actually use. They're the friendly faces on top of all this incredible, complex technology.
So, we've traveled all the way from the big, abstract idea of AI down to these amazing creative tools. But there's one final, absolutely crucial piece to this puzzle: you. Because to unlock the full potential of these tools, the key is learning the art of the prompt. Prompt engineering sounds so technical, right? But really, it's just a fancy term for a simple idea: learning how to talk to an AI. Think of it like giving directions. The more clear, the more specific your instructions are, the better the result you're going to get. It's the new essential skill for getting exactly what you imagine out of these tools.
And here's the good news. Anyone can get great at it. The biggest key is just to be specific. Don't say write about cars. Say write a 3-paragraph blog post about the benefits of electric cars for city driving in a friendly and optimistic tone. Tell it the format you want: a poem, an email, a list. Even give it an example to copy. The more guidance you give it, the better it becomes as your creative partner.
And so that's our journey from a huge, abstract idea about machine intelligence all the way down to a powerful, creative partner that's sitting right at your fingertips. We've basically handed the paintbrush to the machine. So the only question left is, what are you going to ask it to create first?
From the moment you ask your voice assistant for the weather to that, perfect movie recommendation popping up on your streaming service.
Yeah, happens all the time.
Artificial intelligence is just woven into our daily lives now. It often feels a bit like magic, doesn't it?
It really does. But beneath that seemingly magical surface are some, fundamental concepts, powerful ideas that are actually surprisingly elegant when you break them down.
Exactly. So today, we're going on a deep dive. We want to demystify artificial intelligence and machine learning.
Yeah, unpack it a bit.
Our mission is really to give you a clear, structured understanding of these concepts, their history, the key distinctions, and how they're shaping things right now.
And this is all pulled directly from the sources shared with us.
Right. Think of this as maybe your shortcut to becoming truly well-informed. You'll walk away, hopefully, not just with a clearer grasp of the tech that's transforming our world, but maybe some insights that give you a deeper appreciation for the magic.
And maybe some confident talking points, too.
Definitely. For your next chat about tech, okay, let's unpack this.
Let's do it.
So let's start with the absolute core difference, because this is where the fundamental shift really happens. Traditional programming versus AI and machine learning.
Okay.
In traditional programming, what you might think of as rule-based systems,
Yeah.
it's all about explicit instruction, right?
Exactly. It's fascinating how prescriptive it is. A programmer literally sits down and writes every single rule the computer follows.
Hand-coded.
Totally hand-coded. Every condition, every action has to be predefined by a human. The system then operates strictly based on exactly what's been laid out. No deviation.
That really clarifies it. So it's about shifting from telling it exactly what to do
Right.
to letting it figure things out.
Yeah.
Imagine writing a simple program to classify a number as even or odd.
Okay.
You, the human programmer, you directly embed the divide by 2, check the remainder rule.
The logic is right there.
Yeah. The formula is basically input plus those human-written rules equals output. Direct, specific. And it only does what you explicitly tell it to.
Now, compare that with AI and ML-based systems.
Yeah.
This is where the paradigm really shifts.
Big time.
Instead of us coding the rules, the machine gets examples. Lots of examples, inputs and their correct outputs.
Okay.
And it then learns the patterns or the rules from that data. It uses algorithms to do this. The logic isn't explicitly coded by us.
It's inferred.
It's inferred from the data itself. That's the key.
And that ability to infer rules rather than being explicitly told them, that's just revolutionary, isn't it?
Absolutely.
Think about, say, spam email filters.
Classic example.
Right. The input is the email content, the output is spam or not spam.
Yep.
The system isn't told block emails with the word Viagra.
No, that would be the old way. Too brittle.
Instead, it learns from thousands, maybe millions of labeled emails what spam looks like, the patterns.
Exactly. And then it can classify new unseen emails based on those learned patterns.
So the formula changes. It becomes input plus the output data that leads to the machine learning the rules, which then creates a model.
Right. And that model is what makes the predictions. This isn't just a technical tweak, it fundamentally changes how we approach problem solving.
How so?
Well, instead of us trying to codify every aspect of human intelligence or decision-making, we're building systems that can discover their own intelligence, in a way.
Which lets them tackle problems we couldn't even properly define rules for before.
Precisely, like sifting through vast amounts of medical data to spot potential diagnoses, or predicting really complex climate patterns, things that are just too complex to hard-code rules for.
Okay, so we've kind of laid out the what of AI versus traditional programming. But the how we got here is just as fascinating.
Oh yeah, the history is crucial.
When you think about the very first stepping stones for something this complex, what's maybe a surprising early moment or invention that really paved the way?
That's a great question because, yeah, many people think AI is like a 5-year-old thing.
Right.
But you really have to go back, way back, to 1946, actually, with ENIAC.
ENIAC.
The Electronic Numerical Integrator and Computer. It was the first general-purpose electronic digital computer developed in the U.S. during World War II, actually.
Wow, okay, but not AI itself.
No, not AI itself, but its significance is immense. It basically paved the way for programmable machines. It showed that complex computations could be done by machines.
So it set the stage.
It marked the starting point for the kind of computational thinking that is absolutely foundational for everything we talk about in AI today. Without that ability to compute complex things, AI wouldn't even be conceivable.
Okay, so ENIAC sets the computational stage.
Mm-hmm.
But the actual birth of AI as a field, that came a decade later, right?
Right.
At what many consider the crucial moment.
Yes, the 1956 Dartmouth Workshop. That's the one.
Organized by some heavy hitters. John McCarthy, Marvin Minsky.
Nathaniel Rochester, Claude Shannon. Giants in the field.
And this workshop is credited with formally introducing the term artificial intelligence.
That's right. It was the aha moment, you could say. Their objective, stated in the proposal, was incredibly ambitious for 1956.
How was it?
They wanted to find how to make a machine that can simulate every aspect of learning or any other feature of intelligence.
Wow, every aspect. That's bold.
Extremely bold. But that workshop, that gathering, it sparked the initial wave of research in problem solving, logic, symbolic reasoning. It really set the intellectual agenda for the field for decades. It's considered the official birth of AI.
So that's how we got started. But as AI evolved, obviously its branches grew. It can feel like a tangled family tree sometimes.
Definitely. AI, ML, DL, Gene AI, lots of acronyms.
Let's try and untangle that, starting with the biggest term, AI, artificial intelligence. Is that truly the main umbrella here?
Absolutely. AI is the broadest possible field. It's the overarching concept in computer science focused on building systems that simulate human intelligence.
And that includes a huge range of capabilities, right?
Massive range. Reasoning, learning, perception, like computer vision or hearing language understanding, problem solving, decision making. It's all under the AI umbrella.
So examples we encounter daily.
Yeah.
Voice assistants, Siri, Alexa.
Yep. Facial recognition systems on your phone or at airports, even those classic chess-playing programs from way back, all AI.
Okay. Then under that big AI umbrella, we find machine learning, ML.
Correct. ML is a crucial subset of AI. It's specifically about enabling computers to learn from data and improve their performance without being explicitly programmed for every task.
So this goes back to what we discussed earlier, learning patterns from examples.
Exactly. That's the core idea of ML. It learns the patterns and rules from the examples it's given rather than having a programmer spell everything out.
Yeah.
It's the engine driving a lot of modern AI's intelligent decision-making.
And ML itself has different ways of learning.
It does. We'll get into those specifics. Supervised, unsupervised, reinforcement learning a bit later.
Okay. But for now, examples of ML in action. We mentioned spam filters.
Spam filters, fraud detection systems, learning what suspicious transactions look like.
Okay.
And definitely those recommendation systems on Netflix or YouTube. They're constantly learning from your viewing data to get better at suggesting what you might want to watch next, constantly adapting.
Got it. So AI is the field,
Yeah.
ML is the learning capability within it. diving deeper still, we hit deep learning, or DL.
Right. DL is a subset of machine learning, so it's a subfield within a subfield.
Getting specific now.
And it's a really powerful one. It uses multi-layered neural networks inspired, loosely, by the structure of the human brain to learn from data.
And this is behind a lot of the really impressive AI breakthroughs we see today.
Very much so. Deep learning is characterized by its ability to automatically extract complex features directly from raw data, like from pixels in an image or raw audio.
It doesn't need features defined beforehand.
Generally, no. It figures out the important features itself through its layers. It excels with really large and complex data sets because this layered structure allows it to grasp intricate patterns that simpler ML models might miss.
So mimicking the brain's layers helps it learn complex stuff.
In a very simplified, conceptual way, yes. And you see it everywhere. The face recognition on your smartphone, voice assistants, understanding your complex commands, not just keywords.
Self-driving cars interpreting their surroundings.
Definitely. That relies heavily on deep learning for perception.
Okay, AI, then ML within AI, then DL within ML. And then there's the one everyone's talking about, generative AI or Gen AI.
Yeah, Gen AI. This is a specialized and currently very exciting area of AI. It's captured the public imagination for sure.
Because it creates things.
Exactly. Generative AI is all about creation. It focuses on generating entirely new content, text, images, music, even computer code, by learning the underlying patterns from vast amounts of existing data.
So it learns what, say, millions of images look like, and they can make a new one.
That's the basic idea. The key technologies driving this include things like transformer models.
Which we'll talk more about later.
We will. They power systems like GPT-4 or Google's Gemini. Then there are Jan's generative adversarial networks.
Okay.
And the fusion models, which are behind stunning image generators like DLAE and Midjourney.
So it can write whole essays or generate amazing artwork just from a text description.
Compose music in a certain style, help developers write code.
Tools like ChatGPT, DLA, GitHub Copilot, those are all Gen AI examples.
Perfect examples. And people are using them for real-world stuff now, designing social media posts, summarizing long reports, creating unique digital art, speeding up coding. It's pretty wild what they can do.
It really is changing creative and professional workflows daily. Okay, so we've mapped the territory. AI, ML, DL, Gen AI. Now, we touched on ML having different learning styles. Let's pull back that curtain.
Right, the how machines actually learn.
Starting with maybe the most intuitive one, supervised learning.
Yeah, this is often the easiest to grasp. The algorithm learns from a labeled data set. Meaning each piece of training data comes with the correct answer, or label. Input paired with the correct output.
Like flashcards for the AI.
Exactly like flashcards. Question and answer. The goal is for the model to learn the relationship between the inputs and outputs so it can predict the output for new, unseen inputs.
And common tasks for this are things like classification.
Classification, yes, like predicting spam versus not spam, or identifying types of objects and images, and also regression tasks.
Regression being?
Predicting a continuous value, like forecasting stock prices, or predicting house values based on features like size and location.
Okay, so learning with an answer key? That makes sense.
No.
Then there's unsupervised learning. No answer key here.
Correct. Unsupervised learning works on unlabeled data. The algorithm has to find hidden patterns or structures without any explicit instructions or correct answers provided beforehand.
So what's the goal then?
The goal is typically to discover inherent groupings, associations, or underlying patterns in the data that maybe we humans haven't even noticed.
Like finding natural clusters.
Exactly. Clustering is a common technique. For example, grouping customers based on their buying behavior to identify distinct market segments. Or dimensionality reductions, simplifying complex data while trying to keep the important information.
Sounds like exploring a puzzle with no picture on the box.
That's a great analogy. Or like giving a kid a box of unsorted Legos and asking them to sort them into groups that make sense, maybe by color or shape or size, without telling them how to sort. It finds the inherent structures.
Interesting. And finally, the third type, reinforcement learning. This one feels different, closer to how we learn.
It's fascinating, yeah. It is perhaps the closest analog to learning from experience through trial and error.
How does it work?
Here, the model, which we often call an agent, learns by interacting with an environment. It performs actions, and for those actions, it receives feedback in the form of rewards if it did something good or penalties if it did something bad.
Positive and negative feedback.
Right. And the goal for the agent is to develop a policy, basically, a strategy that maximizes the total cumulative rewards it gets over time.
So it learns the best actions to take in different situations to get the most reward.
Precisely. It learns through consequences, which raises interesting questions, doesn't it? Like when an AI like AlphaGo beats a world champion,
Yeah.
is it truly thinking like a human strategist, or is it just incredibly efficient at pattern matching and optimizing its policy through billions of simulated trial and error games?
That's a really profound point. It makes you question our definition of intelligence itself when looking at these systems.
It does. But the analogy is often learning to ride a bike.
How so?
You try, you wobble, penalty, you adjust, you pedal harder, you stay upright longer, reward, and eventually you learn the policy for bike riding through direct interaction and feedback.
Got it. And we see this in game AI, obviously.
Game AI, like AlphaGo or those Dota 2 bots that beat pro teams. Also in robotics, teaching robots to walk or grasp objects.
Learning in the real messy world.
Yeah, and even optimizing complex systems, like traffic light signals in a city to improve flow.
Okay. Supervised, unsupervised, reinforcement. Those are the main learning styles. From there, we move to the actual blueprints, the architectures. The brains, maybe?
You could say that. The key models, especially within deep learning, that make these amazing capabilities possible.
Right. First up, convolutional neural networks, CNNs.
CNNs, these are the stars when it comes to vision. They're exceptionally good at seeing patterns in images.
So primarily for image processing, computer vision.
Primarily, yes. Think of CNNs as having layers that learn to detect features hierarchically. Early layers might detect simple things like edges or corners.
Okay.
Later layers combine those to detect shapes or textures. And even later layers might combine those to recognize objects like faces or cars. It applies these learned filters across the image.
A bit like how our own visual cortex processes information in stages.
Loosely inspired by that, yes. Key parts are these convolutional layers that apply the filters, pooling layers that downsample, and then usually some fully connected layers at the end for classification.
And they're used for?
Things like handwritten digit recognition, a classic task, face detection systems, and increasingly in medical image analysis, finding anomalies in scans.
Okay, CNNs for vision.
Yeah.
And there are recurrent neural networks, RNNs.
RNNs are designed for sequential data where order matters.
Like text or speech.
Exactly. Text, speech, time series data like stock prices over time. They're built to handle sequences and, crucially, to have a kind of memory.
Memory, how?
Unlike standard feed-forward networks, RNNs have loops in them. This allows information from previous steps in the sequence to persist and influence the processing of current steps.
So they remember the context from earlier in the sentence, for example.
That's the idea. They can maintain a state or memory of past inputs. This makes them ideal for tasks like language modeling, predicting the next word in a sentence, speech-text transcription, or predicting future stock prices based on historical trends.
Are there different types of RNNs? I've heard of LSTMs.
Yes. Basic RNNs can struggle with remembering things over long sequences, the vanishing gradient problem. So variants like LSTMs, long short-term memory, and GRUs, gated recurrent units, were developed. They have special mechanisms, gates, that help them learn and remember information over longer periods. They are much more powerful in practice.
Got it. So CNNs for images, RNNs, LSTMs for sequences, and then the big one right now, transformers.
Transformers, yes. These are really state-of-the-art, particularly for natural language processing, NLP, but increasingly for vision tasks, too. They're behind almost every major AI breakthrough you've heard about recently.
What makes them so special?
The key innovation is something called the self-attention mechanism.
Self-attention.
Yeah. It allows the model to weigh the importance of different words or parts of the input sequence when processing any given part. It can look at the entire sequence at once and figure out which parts are most relevant to understanding a specific word or token.
So unlike an RNN that processes sequentially, it can look everywhere at once.
Sort of. Think of it like reading a whole paragraph and instantly understanding how a word at the beginning relates to a word at the end, rather than having to read word by word and hold everything in short-term memory.
That sounds much more powerful.
And faster.
Much faster and more scalable because it can process all the tokens or words in parallel, unlike the sequential nature of RNNs. This parallelization is huge for training on massive data sets.
And these are the foundation of the big language models.
Absolutely. Modern large language models, LLMs like GPT, the basis for ChatGPT, BERT, Google's Gemini, Anthropic's Claude, Meta's Llama, They are all built on the transformer architecture.
So if you've used ChatGPT, you've interacted with a transformer.
You have indeed. Or Google Translate, or sophisticated document summarization tools. Incredible.
Yeah.
Okay, building on that, let's look specifically inside generative AI. We mentioned GANs and diffusion models as key technologies. Tell us about GAN's first generative adversarial networks.
GANs are pretty clever conceptually. They involve two neural networks competing against each other.
Like competition.
Yeah. You have a generator network whose job is to create fake data, say fake images of faces. And you have a discriminator network whose job is to look at an image and decide if it's real from the training data or fake created by the generator.
So one makes fakes, the other tries to spot them.
Exactly. They're adversaries. The generator tries to fool the discriminator, and the discriminator tries to get better at catching the fakes. As they compete, they both improve. The generator gets better at making realistic fakes, and the discriminator gets better at telling real from fake.
Like an art forger and an art detective constantly trying to outsmart each other.
That's a perfect analogy. And the result, ideally, is a generator that can create incredibly realistic outputs.
What can they create?
Photorealistic images, deepfakes, which raises ethical questions, of course, unique digital art. There are tools like ArtBreeder Online that use GANs to let you generate and modify faces, or AI systems creating novel clothing designs.
Okay, that's GANs, and then diffusion models.
Yeah.
These seem to be behind the really high-quality image generators lately.
They are. Diffusion models are relatively newer on the scene, but have produced stunning results. They work quite differently from GANs.
That's so.
The core idea is a two-step process. First, you take real data, like an image, and systematically add noise to it step by step until it becomes pure random static.
Okay, you destroy the image with noise.
Essentially, yes. Then the model learns to reverse that process. It learns how to take the noisy static and step by step remove the noise to reconstruct the original image, or generate a new image matching a description.
So it learns the path from noise back to coherence.
Exactly. It learns the denoising process. And this method has proven capable of producing ultra-high-quality images and art, often with incredible detail and coherence, sometimes better than GANs.
And these power.
Models like OpenAI's DLA E2 and later versions, Midjourney and Stable Diffusion. If you've seen those incredibly detailed, sometimes bizarre AI-generated images online, chances are a diffusion model was involved.
Amazing tech. Okay, so with all this incredible AI capability, creating text, images, code, how do we as users interact with it effectively? This brings us to prompt engineering.
Ah, yes, a very practical and increasingly important skill.
First off, what exactly is a prompt in this context?
Simply put, a prompt is the instruction, the message, the question you give to an AI tool. Whether you're typing into ChatGPT or giving a description to DLA, that's your prompt.
And prompt engineering then is?
It's the skill, maybe even the art, of crafting clear, precise, and effective prompts to get the best possible results from these AI systems.
And why is this suddenly so important? It sounds like just asking a question.
Well, it is, but the way you ask matters immensely. The quality of the AI's output, whether it's text, an image, code, whatever, is directly dependent on the quality of your input prompt.
Garbage in, garbage out.
Yeah.
Or maybe vague prompt in, vague output out.
Exactly. A better, more specific, more well-crafted prompt leads to smarter, more accurate, more relevant, and often more creative results from the AI.
So what are some key tips? How can you, the listener, write better prompts?
Okay, first and foremost, be clear and specific. Don't just say write about dogs. Say write a blog post about the challenges of training a border collie puppy, focusing on positive reinforcement techniques in an encouraging tone.
Detail matters.
Huge difference. Second, mention the desired style, tone, or format. Do you want it to be formal, casual, funny, a poem, an email, a script? Tell the AI.
Give it constraints and goals.
Right. And third, if it's complex, sometimes providing an example helps. Like, here's an example of the kind of summary I want. Example. Now summarize this new text in the same way.
Context and examples.
You really need to think about it. In a world where AI can do a lot of the doing, your unique human skill becomes more about the directing.
So prompt engineering isn't just a technical trick.
No, I think it's more fundamental. It's about effectively translating complex human intent, creativity, and goals into instructions an AI can understand and act upon. It's becoming a critical bridge skill between our vision and the AI's capability.
Wow. That's a great way to put it. Okay, what a journey we've been on.
We've covered a lot of ground.
We really have. We unpacked that core difference between traditional coding and how AI learns from data.
From explicit rules to inferred patterns.
We trace the history from the computational groundwork of ENA.
To the conceptual birth of AI at the Dartmouth workshop.
Then we untangled that family tree. The broad umbrella of AI, the learning engine of machine learning, the powerful networks of deep learning.
And the creative explosion of generative AI.
We dove into how machines learn supervised, unsupervised reinforcement learning.
The answer keys, the puzzles, the trial and error.
Explored the key architectures, CNNs for vision, RNNs for sequences, and the game-changing transformers.
Yeah, the building blocks.
And even peeked behind the curtain of how Gene AI creates things with GANs and diffusion models.
The forger versus detective, and learning to denoise.
And finally, we landed on the practical skill you need now, prompt engineering.
Directing the AI effectively.
So hopefully you listening now have a much clearer map of this complex, fascinating AI landscape.
Yeah, enough to not just understand the headlines, but to discuss these powerful technologies more confidently.
Absolutely. So to leave you with something to think about, given everything we've unpacked about AI's ability to learn, reason, and now even create in ways that surprise us, what new ethical considerations do you think become the most critical as these systems get even more deeply integrated into our work and lives?
That's a huge question. And maybe also, how might your new understanding of prompt engineering of being the director empower you in surprising ways moving forward, ways you perhaps hadn't even considered before this conversation?